Today's lecture is on UML State Modeling. Well, first, why do we model states? So, a system may have many objects, and the objects in a system may have complex temporal behaviors. And for example, there are many applications that are interactive, and also they are distributed. There are many active objects in a system, and they use locking primitives to synchronize the threads and processes and so on. And also in embedded systems, for example, the software control devices and the devices runs in parallel with the controller, and the devices communicate with one another or the controller by the signaling. So there are many design problems. For example, there could be race conditions, and also there are synchronization anomalies, and you may lost expected signals, or you may have unexpected signals, and also you may have deadlocks and so on. So now the question is how to design our system to prevent such problems from happening. Now let's take a look of what potential problems that can happen if we do not carefully design the system, do not carefully model the states. Well, the controller may enter, for example, a state in which it no longer is receptive to signals from the environment. And the signals may arrive, but the controller doesn't receive it. Is not in a state that can receive signals. And also the controller may prevent issuing of signals. For example, the system may gray out the buttons in a GUI interface that you cannot click that button. So, for example, I drove Chrysler 300 before, and at one time, it get into that state. So what I realized is the battery is in the trunk, and I parked my car for a long time, for several weeks, and about more than a month, and then the battery is dead, and then I need to change the battery or charge the battery, but the battery is in the trunk. Then I try to open the trunk, but the trunk is electronically controlled, so I have to click that button. But when I click that, push that button, the button is ineffective because it doesn't work because there's no battery. So you can see this could be a design flaw in that automobile. So another scenario is the controller may enter into a state in which it can receive signals, but the environment doesn't offer that signal. And another example is the controller expects there appears to be in some states, so that can receive some signal, and but it sends the signal, but the peer is not ready to receive that signal. So again, the system cannot work together. Well, many of these problems, they cannot be solved by simply testing. For example, there are race conditions, and so those problems may not occur all the time, and it may occur sometimes, and so it's difficult to reproduce. And also, it is very difficult to simulate all the possible interactions with an environment. And often when we test a program, we are under a lot of assumptions how the users use them, but actually in reality, that may not be true. Alright, so how to deal with this issue? So we have to model the states. So we need to model each entity in a system as a communicating finite state machine, and then we can simulate the interactions between state machines, and then we see whether there are flaws in the system. So the technique that exhaustively analyze a system specified in finite state machine, and to exhaustively analyze analyze all possible states in a system. That technique is called model checking. For small systems, model checking is possible, but for large systems, it's not that possible because too many states basically. All right, so let's take a look at what is finite state models. Basically, describe the temporal and behavior view of a system, and then you need to specify the sequence operations in response to some stimulus. And you need to distinguish there are three concepts: states, events, and transitions. So that's basically UML state diagrams. Alright, so what is an event? Event basically occur at a some time point that's instantaneous and often responds to some verb in past tense. For example, alarm set and power down, for example. And another example, type of event is the onset of a condition. For example, the paper tray becomes empty. The moment that it becomes empty, this event happens. All the temperature drops below zero, and the moment that the temperature drops below zero, this event happens. So this event happens instantaneously. It takes zero amount of time. Of course, that's as we said, this is a model. We extract the details. So we treat event that takes zero amount of time. That happens at a point in time. So state are behaviors, the condition that persists in time. So state means that this thing lasts for some time. For example, the water is boiling, or you are waiting, or you are dialing a telephone, for example. So in object-oriented terms, the state is an abstraction of the values of the attributes and the configuration of the objects, basically. Now transition. Transition means the instantaneous change in state, from one state to another state, and it's triggered by some event. Okay, now let's take a look at state diagrams. So UML state diagrams basically the graphical representation. We need to represent the states. The states basically labeled rectangles, and we need to label the transitions by basically these arrows. So this is the source state, and this is the target state. So from this state to this state, so there's a transition, and on the transition we can label event with some attributes, and also label some condition. So here's we use this represents the condition and slash the effect. So the transition is enabled when the source state is when we are in this state, and also the condition is satisfied. So when the system is in this editing state, for example, and when the form is complete, when this condition is satisfied, and then this event happens. So and then when this event happens, then the system translates to another state called summated state, and then this slash display a pop window which is the effect of this transition, Alright, so now let's take a look of different kinds of events. One type of events is signal events. So basically they occur as a signal. It's explicit one-way transmission of information, for example, and may have parameters, for example, string enter and so on. And also you need to understand that sending a signal and receiving a signal are two different events. For example, the flight departures and button pressed or string entered and some digits dialed. So this is a signal event. Another is change event. Change event means that the satisfaction of Boolean expression. For example, that basically means that when some Boolean expression is true, then this event happens. For example, when the temperature is below 0, and when the temperature is less than some minimum, when the tire pressure is less than some minimum pressure, or the time equal to November 2027, for example. So you can see that this, and so when this Boolean expression is true, then this event happens. So basically, you can assume that this expression is continuously tested, and when it change from false to true, then this event happens. The third type of event is called time event. It means that after a certain amount of time, then this event happens. All right. So activities. So within a state. So when they are within a state, there are times that you enter this state, and there are times that the system stays in this state, and there are times that the system leaves this state. So we can specify some activities that corresponds to these three three. So one is entry. You can write entry / and then this is the activity the system will perform when the system enters this state. And you can write exit / something, some activity. This is the activity that the system performs when the system leaves this state. And you can use do / something, some activity. That means that these activities are performed by the system when the system remains in this state. All right, so there are two sources of state explosion. So one is there are multiple transitions with the same triggering event, guard conditions, and also effects. So, but with different source or target states. So, and the solution to solve this is by state generalization. And another source of state explosion is by due to concurrent or orthogonality among different objects in a system. Now let's take a look. And the solution to solve this type of state explosion is by parallel composition. All right, now let's take a look at this example. So we have this is a transmission system in an automobile. So initially the system is in a neutral state, and then when you push R, means to push R, and then you go to the reverse state. Then the system goes to the reverse state, and push N to go to the neutral state, and then this neutral state push F goes to the first gear, and upshift to go to the second gear, and upshift to go to the third gear, and third gear downshift to the second downshift to the first. And at any state you can push N, that will go to the neutral state. So what you can notice is that these three are the same with the same name, right? So only the source states are different, and the destination states are the same actually. So we can use state generalization to reduce the complexity. So what we do is basically we put this first in the first gear, and second gear, and third gear. These three we call forward state. So this is a super state. So we call forward. And in a super state, you need to have an initial state. So from any state goes to this neutral state means that goes to this super state means that go to this initial state, and leaves any transition that leaves this super state means that leaves from each of the state in the super state. Okay, so basically that's what I have said. So this super state basically includes multiple states, and the outbound transition that basically the transition leaving leaving the super state means that you have one transition leave from each of them, each state in the super state. And for any state that coming to the super state means you come to the initial state, and here use this dot indicate this is an initial state for the super state. And this is another example for the life cycle of a thread. So in the beginning, a thread is created, and then you start this thread, and then thread is in the runnable state. In this super state, and in this runnable initial state is ready. And when dispatched, basically the operating system schedule this thread to run, then this thread is in a running state. And then after you run some milliseconds, then you need to yield to another state. So then you need to yield to another thread. So the operating system schedules this out. So this is called yield. So the running for this thread, its state transits from running to ready. And at this running state, if suspended, for example, need to wait for some lock, then it's blocked in this block state. All right, and so for the state leaving, and in the running, if finished, then you got terminated. And for this, when the system is in the super state, if you kill it, for example, stop it, or from the beginning or from this block, if you kill them, then they will be terminated also. And from this block, for example, if this thread is waiting for the lock, and when the lock becomes available, then it resumes. So you can see that for this resumes, which means that you first enter this ready initial state, which means this thread becomes ready. And this stop, which means that you can kill this thread from either in ready or running. So this stop is leaving this super state, which means that you have a state that you have a transition leaves from each state in this super state. So we have from ready, if we stop, we go to terminated. From running, we stop, we go to terminated. And if you want to specify some transition from a specific state within a super state, then you just directly leave from that state and go to a target state. All right. So another source of state explosion is this orthogonality. It's basically a system may have many aspects, and they are orthogonal to each other. Now let's take a look at this automobile example. So in an automobile, you have automatic transmission, and you may have temperature control. You may have rear window defroster. You may have a stereo system. And suppose that we want to construct a state diagram for this automobile. And we can assume that the car starts with when the transition is in neutral, and the temperature is off, and the rear defroster is off, and the stereo is off also. So then what's the possible next state? There are many possible next states. For example, if you push heat, then the heat is on, the neutral is still in neutral, is still defroster is off, still radio is off. And if you push air, the air is on, still in neutral, and defroster off, and radio off, and so on. So there are many possible next states. So to deal with this problem, because this temperature control and rear defroster and radio control are orthogonal components, whether you turn on this rear defroster or not has nothing to do with whether you are listening to the radio or not. And when you listen to the radio or not, it has nothing to do with you turn on the temperature control or not. So the right way to deal with this, to reduce this complexity, is to decompose the system into multiple subsystems, and you model each subsystem individually. For example, we have this rear defroster. We push rear defroster on, then on, push it off, and the radio is also turn on, turn off. Okay, and similar for the temperature control and so on. Here the temperature control is the temperature in this super state, the temperature is on, and when the temperature control is on, it could be in cooling and could be in heating, and could be in any of those. So it's hard to decide which one is the initial state. In this case, you may not have an initial state. All right, so in cooling, and you push heat, it will be heating, and push air, become cooling, and when the temperature control is off, and you push air, you turn to cooling, and you turn heat on, it's into heating, and you push the temperature control off, then the temperature, it enters into the state of temperature control is off. So when the temperature control is off, so you can see that it doesn't matter it's in cooling state or in the heating state. So this condition, this transition, it leaves this super state. So it's equivalent to, you have two transitions, one from cooling, push the TC off, another from heating, push TC off. Both destination target state is temperature off. Alright, so the homework reading assignment is to read the UML textbook, the state modeling.